After we test the symbol, we need to go back to the symbol. Let's close this one. Do you want to save? Let's say yes. So this is no. Okay, we go back to the, not the test bench, the inverter that we created. We open the schematic. So we need to create a layout for this one. We go to launch, layout Excel, create new, leave the same, then leave the name as it is. Layout, make sure it is layout. Okay, open the layout. Then you can go to this bottom, which is generate all from source. Leave it the same. Okay, so now it gives you the boundary, the two transistor that we have, and it gives you the input. Let's delete this. We don't need it. Take those two, M, you can make it up, M. So make sure that the MMOS is up. This is BMOS is up, and this is the input. You can get rid of this dot by press E, then type none, because I don't like it. If you like it, just leave it. Now it is like so clean. M, take this one, make it like aligned properly with the true transistor. So now this is source, this is drain. You can sweep it from the properties. Is the same drain, so we need to connect the drain together, and S to the ground and other S to up, and we need to have a body. So this body is connected to the source, and this body is connected to the source, but here we don't have body, so we can press on it, Q, then you go parameter, go up down. You can switch between source and drain, so make the source left and source right and drain left by click this one, but we don't need it in this case. Let's make the body on the left, which is this one, and make it integrated. That means attached to the source. Okay, make it okay. So now this body is added. Let's add this as well. Q, parameter, make it in the integrated on the left. Let's see. Yeah, perfect. So now let's connect this. The blue is the gate. Let's connect by click or hit P path, and you can connect it, and it is automatically will take the same layer. So now this is the poly. So take the poly, and this one is the source. Just make sure it is connected properly. Okay, perfect. And this one we need to connect it to the ground. Let's create by a ground by choose the metal is M1. Okay, it is already there, and hit R. That means you can create rectangular. Why taking time? Okay, go here, R, go until here. So this R. This we make it like common ground. Then copy it. This C. Then you can copy it and put it in the upper for the common VDD. Now you can hit P, have path connected to the ground, make sure it's connected properly. And the same thing with this one. Okay. Okay, now this we take output from here, make it here. And now we need to have the output, but the poly cannot be as an output because the poly uh, is the below the middle one. In order to make it up, we hit O for via, then we choose the via take you from layer to layer. So we need to have a layer. It's like stairs, like floor. And the below OD is the below, then upper is PO, poly, then middle 1, middle 2, 3, 4, until the last floor, upper floor, it is AP. Just imagine like this one. Choose this one, make it one by one. You put it here. Let's press this one. This is prevent you if you go closer, it will give you their error. So you cannot put it here, not here, not here, not here, but you can put it here. Okay, let's make it here. Skip. Okay, perfect. Let's go P or path and have the output. Okay, everything is set. Let me make an error because I want to show you how to have an error. And okay, let's make this. Okay, let's ignore this one. Okay, let's save it and check. Now, after we create that out, so we have the output here, input here, the VDD and ground. In order to make sure that there is no error, there are a file called DRC, design rule check. So this file will check if your design can be fabricated in the foundry or not. For each foundry has its own file on the design rule check. So we have the TCMC file. Now let's go and check it if there is any error before you send it and pay money and lose that money or not. Okay, so here we navigate to our file where is the TCMC is. It is, you can go to the SW, then opt, then share. Cadence. We have Cadence synapses, but now we are using Cadence. We go the kit, then the technology 65, then you go Calibre, then design rule check DRC. Then you choose this file calibre.drc. Okay. Input. You need to make sure this is export from layout. Output. What is this? Make it, leave it the same. Okay. This is all. Don't show again. And okay. Okay, these are the error giving. Some error can be waived because when you integrate everything together, you can waive the error, but some of them is cannot. For example, this one, it says area on the edge length is lower than 0.8. So we have here 46 error. Let's go and see how can you fix this error. Okay, you can click in here and it will take you to where the error is. Let's go back to see what he said. It says NW, it's like NWell, this is NWell, is less than 0.8. It should be bigger in terms of micro square. So this one, it is give you the head. So you can go here, type in W, choose the NWell draw, then R. Now we need to make this is like because it should be like the ratios is compatible. Okay, save. Let's check another error. So any density error you can ignore. This will be waived, and by the end, when you integrate all the circuits, it's gonna be waived. Also, this DOD it can be waived. Floating gate can be waived. This VTL can be waived. This is cannot be waived. Okay, this is says the PP, PP or NP enclosure of PO. So any poly should be on top of PP or MP. Cannot be in the nothing below it. Okay, so here it says the poly is not underneath the poly is nothing. So we need to have either the PP or PN. Let's make PN. Is it PN or MP? MP. Yeah, MP. Then may R. Then you can take it from here, no problem. So let's make it here. Okay, save. Let's go again. Here there is another problem. We can do the no. This is density problem, so no worry. Okay, CSR you can ignore it. ESD you can ignore it. Okay, now the error is 46. Let's run again and to see how much error we fixed. I suppose 42, 43, maybe 44, 44. Okay. So here density problem, density problem. Okay. Okay, everything is solved. So let's go now to the LVS. LVS is another file. So that now what we did, we checked that the machine in the foundry, it has the capability to do the minimum feature. So for example, they need to do a tranche or a wire. The machine, the minimum can do is like one, for example, 1 micron. But if you give them half micron, so the machine cannot do it. So by using DRC, we can see that the machine it can be fabricated. Now the LVS, this is another step. So now this step is it will check the connectivity between the schematic that we did versus the layout. That means layout versus schematic. So if there is wire and here you missed it, so it will, this file will tell you that there is a wire missing, so you need to come back and do it. This is another useful things. Okay, so let's go to setup and make the input and the output row. Let's choose it from here. Okay, where is it? It is opt share cadence. This Calibre LVS. Now we take this file. Okay, input, make sure to export from layout, export from schematic viewer. Do we need to change this? No. The output, okay, LVS here, make the VDD, the power net that we have, which is VDD, and the ground G and D, always make them capital, then run. Don't show, okay. Don't show, okay. Okay, so it's here. We need to see here. How can I make it bigger? So here it's X. That means it's incorrect. There is some problem. We need to fix it. How we fix it? We go to the file itself. Let's close the DRC. Let's finish from it. We go here, comparison. So now it gives you that. It says the net, the layout is 4 and schematic is 4. The instant one is 1. The port in the layout 0 and schematic is 4. That means there is 4 port is missing in schematic. So we have 4 port schematic, but we don't have it in the layout. In order to have it, we can write L. Then we can go use the same layer. Make this smaller, 0.1. Make the name VDD GND out in. I think everything is okay. Let's check. Yeah, this is VDD. This is automatically, it will give you the exact. So if you put it up to the in the top of the poly, it gives you the same layer. So that's why I put it automatic. We put this here. It can see 2, the PR boundary and metal 1. We put it in button 1. What's the next? Ground, the same thing. Metal 1. Out is here. Put it in metal 1 and metal 1. Let's save it. Go back again. This is LVS. Run LVS. Hopefully you can see that smiley face, not the sad face. Okay, so we have the same problem. It didn't see it. Ah, okay. This is the problem. So we need, so now when we put this L, we give them draw. Actually, we need to give them pin, not draw. So it still cannot see it. So let's go here, Q, make this as a pin. Okay, make both of them. Let's see if we can change all of them in the same time. Yes, we can. Okay, choose this one. Okay, before you need to save and check. Then let's go again, run again. We need to see that's the face that is smiling. Hey, we find the smile face. So now if you can see the port, it is 4 and 4. Now, after we check that all port, all instant, all net, it is compared with the schematic, it is there. So we can go and do the final check, which is the PEX. Not final check. Now we will make this as a capacitor, because in the reality what the schematic did, in the schematic we measured the performance just with the numbers inside the transistor. We didn't measure the effect of the wire, because any wire close to each other it make capacitor. For example, this and this, there is a capacitor between those and those. But here now we will test it, just the transistor parameter and plus the wire, the capacitance, the parasitic capacitance, and the resistance in the wire. So we need to test it. We need to create the model extract the model from here. Then we take it back to the test bench. Then we can test it. Now again, we can go to rule. Okay. Okay, now let's go to RCX. Then we choose the caliber. Also set up PEX input. I want to do something because you might have this problem. Let me delete, not this one. We were here. Let me delete this one. This one. Delete. Then shadow row. This one. Okay. I need to delete this one. Do not delete the things that I did because I want you to, because I had a problem before and I fixed it, but now it is fixed on my side, but I want to go again over this problem. So do not go and delete that rule things, but I will show you what the problem you might face and how to solve it. Yeah, this problem. You might have this problem. How to fix it? It says that error while compiling rule file. It gives you this name, and it says that problem with access. So you don't have access to this one. You can fix it by change some in the file itself, the DRC, change some line, or you can go, this is easier, you can go to where is the file located. Let's see, it says SW share 60 caliber R6 here, so it gives you the path. So you can go navigate. SW opt share cadence kit 65 caliber RCX, and take the file rule from here, copy it, and put it where did you open your file. So I'm opening I create this file, inside it this file that I'm using. So you can put it here, paste, then go back again. Let's see if it's give you the same thing or not. Let's close it to see again. Let's save this, copy, close, no, do it again. Cancel, load. It's easier to have it from here. You can save this one, but I didn't save it because I want you to to go through it. But once you go through it, then you can save it, and every time you can load this setup. So here, take this Calibre RX. Okay. So here you need to, I believe you need to share to copy this. Copy, make it inside the file, paste. And just remove it from here. Search. Okay. Input. Make sure it is GDS. Netlist export. This we don't need to change it. The output. So this is what you want to measure. Decoupling capacitors to ground or resistor. So we need the decoupling capacitor and capacitor between the wire. Here you make it cell caliber view. Index option. Okay, where is the output and input? Here LVS option. Make VDD as a output, as a power, and ground what we use already. Okay, don't show. Okay, don't show. Okay. Okay, so here you can see that the box for the parasitic capacitance view, nothing inside, so you need to make the path for this. So you can go here. So you need to have this cell view. Go property. You can navigate. You can find it here if you don't know how to find it. Okay, how can you make this bigger? You copy this to make it easier. Copy. Go here. Get it here. Paste. Okay. Then make sure it is open. So you need to find all the cell map here. Make a schematic. Create terminal. This is up to you. Array or location. This is up to you. Read mode. Okay. So now from the wire itself, they are creating this capacitance. They measure the value and they created this capacitance for you. So now you can have like an inverter which is with the capacitor that it might affect the design. Now close it. Okay, so now I want to save it. Okay, I don't want to save it. You need to save it for you. Okay, so this is the layout. Let's close this one and close this one as well. So let's go to the test bench now. Is it open here or close it? Okay. Let's open the test bench. Now we need to test it without Calibre and with Calibre. So last time, I don't know, is it load? Can we load it from here? Load. Ah, perfect. So this one for the last time we did. So this is the end. We don't care about it. We make sure that. So this is the out. We can make the width from here. Style make solid. So okay. So now make it a bend, and we want to test the caliber after adding the parasitics. You go here, right click, environment, go in the beginning and write Calibre space. So now So now the simulation will go to the once you start the simulation, we'll go to this Calibre. If you find Calibre model, it will simulate it. If not, it will go to the next one. If not, it will go to the next one. But you can see that we already created Calibre. We created Calibre model. So we'll go this first, and then we go to the spec for this one. Okay, so we said okay. We minimize this. Now we need to simulate and compare between the design without taking in account the parasitic capacitance, the wire that add more parasitic and resistor, and after we consider that parasitic capacitance. This is a small circuit, small inverter, so the effective of this inverter will not be high. But once you have big circuit, the OTA is considered as like medium size. You can see how can you design your circuit, because once you do the layout, you need to make sure how big the wire that you need, how far from each other. Also, there is parasitic between layer and layer, like floor and floor, not next to each other, on top of each other. So you need to take the account of all of those things. If you are interested about layout, let me know so I can share with you some sources, some papers, some books to help you to design the circuit not for this project. Once you finish and you have other project, you can contact me and I will send you the useful resources. Okay, you can let me try to write my email so you can contact me on this one. abdullah.asharhari.edu. So you can contact me in this. So here we have 4 things. So replace, if I choose replace and draw the graph, it will remove the old one. But for me, I want to compare the old one with the new one. So I will be append. So it will draw the graph on top of the old one. Okay, let's draw the output. Okay, so the output is in here. Let's make it style solid. The width medium. Okay, so let's see if they are identical or the same. Okay, if you can see, this is the without the effectiveness of the parasitics, and the green one is after the effective. So there is some delay. If you click A, then B, so you can see there is 5 picosecond delay. Now this is more close to the reality. So for the project, if you want to go to the layout, I want to see the output with and without the parasitics for your OTA. And thank you for listening and good luck with the project.